Let's start with a simple linear regression model. I'm going to model the relationship between prestige and education. This is my sample regression model. I'm going to estimate beta node and beta 1 using the data in the prestige data set. You can use LM function to fit a linear regression model. Here LM, this is your y variable. Then you have to give tilde mark. Here you have to specify your x variables. And under data argument, you have to give the name of the data set that you're going to build the model. Remember, at the beginning, we split prestige data set into a training set and test set. We only use training data to build the model. We're not going to touch the test set. So that's why here I pass train. In order to view the results, you can use summary model 1. Here the name of this, the output of this function is stored under model 1. So in order to view the corresponding output, you have to pass summary model 1. So here you have summary statistics of residuals. Here you have the description of coefficients, their estimated value, standard error, t-value, and the proper p-value. And here you have some statistics related to the overall accuracy of the model. Residual standard error, multiple r squared, adjusted r squared, f statistics, those things. This output is kind of messy. This is not a tidy format. This is not a tidy data set. What's messy about the output? If you want to extract the coefficients, it takes multiple steps. First, you have to calculate the summary of the model, and then you have to extract the coefficients from the output. Then you have to store it under a data frame. So, for example, this is sometimes you need to extract coefficients and store it under a data frame if you want to visualize these estimated values along with their standard errors. Because in order to use the ggplot, we need to have all of the data in one single data frame. So with this output, in order to arrange the coefficients under a data frame, it takes multiple steps. So that's probably an indication that the original output is kind of messy. The second one is column names are inconsistent and inconvenient to use. So for the first column name is estimate. The second one is std dot, then we have a white space error. Next one, t white space value, and these has several other notations. So column names are inconsistent, because of that it is inconvenient to use. And the last thing is information are stored in row names. So for example, intercept and education, rather than arranging those things under separate columns, they are taken to name the rows of this data frame, this part of the data frame. So the rows of the data frame here are named by intercept and education. But these are actually information that we want if we want to use the tidy tools on top of this. We can use Broom package to convert your model output into a tidy format. Broom takes model objects and turns them into tidy data frames that can be used with other tidy tools. Broom defines tidy methods for extracting three kinds of statistics from an object. They are component level statistics, observation level statistics, and model level statistics. Let's go back to the previous slide and observe these components. For each and every observation in our training data set, they have a residual value as well as a fitted value and some more. They are called observation level statistics. So this here we have the summary statistics of residuals. So this is related to observation level statistics. And these ones here are called component level statistics. The information related to beta naught, beta 1. And if you have multiple linear regression models, information related to all coefficients related of each and every regressor. And these one up here are called model level statistics. Let's first look at the tidy function in the Broom package. Tidy function in the Broom package convert component level model output into a tidy data frame like this. So model 1, pipe operator tidy, or else you can write this one as tidy inside brackets model 1. This is just one function call, not like this. Now the information stored in columns. So now they are not row names, they are stored under a column called term. Furthermore, here instead of complicated notations like this, we have p value, p dot value, no white spaces. When you have white spaces in column names, sometimes it creates problems when dealing with other tools. So this is a convenient column name rather than the one before. Here each row is a coefficient. This is estimate, standard error, t-test statistic value, and p-value. Recall the definition of standard error. The standard error is the standard deviation of any point estimate computed from a sample. Here, the standard deviation of the sampling distribution of beta 1 hat is called the standard error of beta 1. Similarly, we can interpret standard error of beta naught hat. If you pass conf.int true, you will get the 95% confidence intervals of beta naught hat as well as beta 1 hat. If you want to select term and estimate, now you can use the functions in the dplyr package. Select, you have to specify the names of the columns, term and estimate. This part of the code will create this output. Now you pass this output inside the select function as the first argument. Furthermore, you have to specify the names of the columns that you need to extract. They are term and estimate. Based on these component level statistics, now you can write the fitted regression model. That's y hat minus 9.42. This is beta naught hat, and this is beta 1 hat. And here xi. Next question is, why are tidy model outputs useful? So actually you might be wondering why it is important to arrange model outputs into a tidy format. The reason is we can use a tidyverse package functions on top of them. For example, ggplot function can be used to visualize model coefficients. Here I plotted the point estimate along with confidence intervals of the beta node and beta 1. Here this corresponds to intercept. From this previous slide we identified the lower level is minus 17.2 and the upper level is minus 1.62. You can see that it's drawn here. This is minus 1.62 and this is minus 17 point the rest. And this is the point estimate of the education, that is the point estimate of beta 1 hat, point estimate of the coefficient related to the variable education, and this represents its confidence interval. You can see the confidence interval of beta 1 hat is smaller than, confidence interval of beta 1 is smaller than the confidence interval of beta naught. Next, visualize the fitted equation with data. Like this. We had data. Now this is our fitted regression model. It is this one. In order to draw the fitted regression model on top of this scatter plot, you can use this code. Here, the name of the data set, that is train. And my y variable is prestige, x variable is education, geom points, that will add these points, and I have added alpha transparency to view through the points. If you have overlapping points, then you will get a dark color like this. There are a couple of overlapping points, that's why this one is a bit darker than the others. Here I use geom smooth function to draw this linear regression line. So the method is LM. If you do not specify a if you do not specify the method as LM, then it will use nonlinear. It will use some other approaches like GAN models to capture the nonlinear relationship. So here, if you want to plot the linear regression model, just pass LM. Here standard errors false, then you can't see the standard errors. If you put standard error true, you can view the confidence band as well. If you want to change the color, you can pass it here. I have changed the color to forest green, and by using LWD, you can change the line width. Next, we want to measure the strength of the fit. We can use model level statistics to evaluate the strength of the fit. In order to extract model level statistics, we can use the glance function. Glance outputs model level statistics. You can see R squared value, adjusted R squared value, F statistic, archaic information criterion, and BIC, log likelihood, those things. Glance outputs model level statistic. We can use coefficient of determination, that is R squared, to measure how well the model fits the data. R squared is the proportion of variation in Y that is explained by the regression line. This is usually reported as a percentage. So this is 74%, 74.1%. In multiple regression, R squared is not a good comparative statistic to evaluate models, because in general, R squared always increases when a regressor is added to the model, regardless of the value of the contribution of that variable. Therefore, it is difficult to judge whether an increase in R squared is really telling us anything important. Hence, we use adjusted R squared. The adjusted R squared will only increase on adding a variable to the model if the addition of the variable reduces residual mean square. Because of that, adjusted R squared is more appropriate when evaluating model fit. In order to extract adjusted R squared, you can use this command: glance model 1 $adjusted R squared. Or else, this is by using base R. Or else you can use tidyverse functionalities like select function to extract adjusted R squared. You should now extract variables by using both base R functionalities as well as tidyverse functionalities. Here, roughly 73% of variability in prestige is explained by the variable education. Next is residual analysis.